Welcome to 6.5e. This is we're going to learn about the general form. So we're going to put it all together. And so what's being pointed out here are things that you're already been exposed to. What we know is that this right here, this A on the outside, is going to adjust the amplitude. So if A is negative, the graph's going to be flipped around the x-axis. If B is negative, it's going to be flipped around the y-axis. B is negative there. The variable A will help us to know how high it's going to go. B will show the period adjustment. We got to be a little bit careful there as we go through there. So it says the variable B. If B is equal to 1, the period is 2 pi. If B is not equal to 1, then the new period is 2 pi divided by B. The variable D causes a vertical shift. So the D causes us to go up and down. And the ratio of C to B is the horizontal shift. That's what we had to be careful of. So for example, let me just make something up. Y is equal to 2 sine 3x plus 6 plus 8. So what we would have is our sine function with an amplitude of 2. It would be moved up 8 units, and its new period would be 2 pi divided by 3. All of that's right. But its vertical shift, right? I'm sorry, its horizontal shift is what I should say. Its horizontal shift is C over B. It's 6 over 3, or 2. And so this is not moving 6 units to the left, it's moving 2 units to the left. And so that's what they'll call a phase shift. It's very hard to graph phase shifts sometimes. He might give you some exposure here, but there wasn't a lot in the homework, and I didn't choose one for the exam. So here's an example, and let's take a look at this. So our example is to graph 3 sine of 2x minus pi. So you would want to factor out that 2, which he does right over here, because the real phase shift is pi over 2 to the right. So A is positive, so there's no reflection. B is positive, so there's no reflection, which is great. So A is 3, so you have a new amplitude of 6 really, but well, the amplitude is really from the middle line up. But anyway, so it's going to have a min and max of 3. A vertical shift is how far it's going up and down. There is nothing being added out here, so there's no vertical shift. And then the C over B relationship from the original is right here. It's a pi over 2. And so the pi over 2, it's shifted to the right because this guy's negative. So we're going to shift pi over 2 units to the right. And remember, this adjusts our period, this 2 out here. So our new period is just pi. So the critical roots, before with sine, it was 0, pi, 2 pi. Now we want to make sure that we get those same critical roots. So notice what he's doing here. He's setting 2x minus pi equal to 0. And so he's adding pi to everyone and dividing by 2 to everyone. So these are our new critical values. What does that mean? It means that we're done. It means that we're starting at pi over 2, right? Because sine starts at 0. And we go up, down, and up. Now remember, our new heights are at 3, right? So this is at the 3 level, and this down here is at the negative 3 level. This is pi, and this is 3 pi over 2, giving us a period of pi really. And so it's been shifted and all of that. So this is a great way to go about it, to get those critical roots and just draw it off of that, and it will mirror that thing. And so you can see that we've drawn the exact same thing as what's there. So example 2 has an amplitude of 4. We're dealing with cosine now. We're taking the original cosine function and shifting it to the left. We should end up with a function that's shifted left pi over 6, and that has a period of 2 pi over 3 is the period. and it's going to shoot left. It's going to go up. Apologize, it's not going to go up 4. It's going to have an amplitude of 4, but not shifted at all up and down. All of these are just phase shifts. And so there's where he's arguing the 2 pi over 3. So what would be good? What would be good would be for us to remember our cosine graph, because that's what's being adjusted. Our cosine graph had zeros at minus pi over 2, pi over 2, and 3 pi over 2, right? Those should be pointed out down here. And now what are we going to do? Easy. We're going to set that original 3x plus 2 equal to all that. I'll go up here where you can see that a little bit more clearly. We're going to figure out where this root moves. So you're just aware that there's a phase shift, but the algebra shows you how to accomplish that. This negative pi over 2 has to move in accordance with this. Okay, so remember, this is negative pi over 2, pi over 2, and 3 pi over 2. So I'm worried about this one right here. And so we're going to subtract over pi over 2 and get 3x is equal to negative 2 pi over 2, or 3x is equal to negative pi. So x is equal to negative pi over 3. That's one of your very first starting place, negative pi over 3. Then you're going to do it to pi over 2, right? So if we wanted to go and get this next root and see where it moves, well, that's easy. We just have to take 3x plus pi over 2 and set it equal to pi over 2. Subtracting pi over 2 gives me 3x is equal to 0, which gives me x is equal to 0. So this new one right here is 0. And then if I wanted this last one, 3 pi over 2, I set my 3x plus pi over 2 equaling 3 pi over 2. Subtract it off and get 3x is equal to pi, or x is equal to pi over 3. And so that should be what he gets down here. So let's go watch him do that. I just want you to see where it happened. So negative pi over 3, 0, and pi over 3. So what do? You don't panic. You just come right down here and draw it. Labeling where you start as negative pi over 3, 0 in the middle, and pi over 3 in the end. And then make sure you get your heights up at 4. Right, because there is that number. With paying attention so much to the phase shift, it's easy to forget about that number out in front, but we're not going to, and get a 4 and a negative 4 out of that guy. So it should just be a quick sketch in all of that, and we're just paying attention to the phase shifting that's going on. All right, so now we're going to look at some things where we got a negative going on. Let's see how that's going to work for us. So let me make this smaller so it all fits on there. And we'll just read this one through. So we got a graph negative 4 cosecant of 2x minus 3 pi. So the a is negative, which means it's going to be reflected in the x-axis, right? And b is positive, so there's no reflection in the y-axis. The 4 is out front, so we're going to have a minimum value of negative 4 and a maximum value of 4. And there's no vertical shift, nothing's being added after the fact. And our new period is our horizontal shift is 3 pi over 2, and it's to the right. Again, when you set those equal to 0, that's going to take care of itself. Our new period is just pi, though, because it's the original 2 pi divided by the absolute value of b. Here's b, and so it's 2 pi divided by 2. And so if you remember that the cosecant function is related to sine, it's going to have zeros at the exact same place. These aren't its roots, actually. These are its asymptotes, right? So this is probably best stated as asymptotes, not critical roots, because that's where its asymptotes are. It has no roots. It's cosecant, never touches the x-axis. So we're getting new asymptotes. How? Just by setting that inside piece equaling to the original asymptotes for the original cosecant function. And so we get 3 pi over 2, 4 pi over 2, and 5 pi over 2. What you'll see down here is 3 pi over 2, 4 pi over 2, and 5 pi over 2 being asymptotes. Now, remember, cosecant went like this, But because of the -4, it's going to flip around that x-axis. That's why it goes low and then high. It's taking into account that negative sign. And notice that they've labeled these beginning points as 4. That's what I would suggest as well. And so here we go again with the graph of y equals 3 times sine of -2x minus pi. And then if you factor out the -2, remember to change that sign to be positive. Let me get a darker color going on for us here. That sign is going to be positive, or at least the opposite sign of what it was. So what do we have? We have an amplitude adjustment of 3, so we know our peaks and valleys are going to be 3. Sine of -2x, x plus pi over 2. So it's going to be reflected about the y-axis. Okay, I don't think we have to worry about that too much, but let's see what happens. No vertical shift, so you know what's going to happen. They're going to identify the period's just pi. They're going to identify the roots of sine, 0, pi, and 2 pi. Set the -2x minus pi equal to those, and come up with 3 new numbers, -pi over 2, -2 pi over 2, and -3 pi over 2. And all they're going to do is graph that coming out. Now, how should that be? It should be the exact opposite of what sine was in terms of flipped around the x-axis. So if we remember our original sine function looks like this. And what's happened is we've moved it back, right? Because we're going to end up shifting it. He has this backwards. This should say to the left. C is not positive. Well, I'm sorry. C is positive, so it shifted to the left, right? I shouldn't have used the word right. It shifted to the left, correct, right? There I went and did it again. If I go back up to the original first page, if we look at the shifting, a positive value moves it to the left. It's right there. So a little bit of a mistake there coming through. Let me see about where we were at. Okay, we weren't that far yet. Yeah, we're right here. So we're going to shift it to the left. So it's moving to the left, and you'd be like, well, why is that hump not up here? Because of the negative sign. Because we flipped it about that x-axis, it gets flipped just like that, and so it gets turned about that x-axis. And so you could test points to make sure you've done it well. Why does the new graph appear to have been reflected about the x-axis? And it's because of this. It's because of it being an odd function. And so that's what he's trying to show you, is that sine of x and sine of -x. So it does look like it's been flipped around the y-axis as well. It is truly a reflection around the x-axis, but it looks the same because sine's an odd function, what you studied before. So they're just trying to make some connections there. Now, this is awesome. Sine x plus 1, no problem. Everything just gets shifted up 1 unit. Sine x minus 2, everything gets shifted down 2 units. And so they're usually pretty easy to understand. Here's what I would recommend. I'm going to do here's my x-axis. So here's the regular sine function, right? Going up like that. But what's happening here is it's shifting down 2 units. So this is now the 2 units down. So here's what I would recommend doing. I'd recommend doing it in pencil, so you could get rid of that axis, and then call this -2 because you just shifted that down 2 units. You know it has a maximum value at 1, right? And so so we're going to shift that down 2 units. So this is our sine function shifted down 2 units. Something's a little bit off. This is only being shifted down 1 unit. Okay, so this is not the right graph. We're shifting down 2 units. So he graphed the 1 in there. Look at, he has a +1 going on there. It's all messed up. Down 1 unit, plus 1 doesn't move it down 1 unit. So let's go off of the original. It's down 2 units. So it has an amplitude still of 1, right? Still goes up. So this is -1, this is -3, and our x-axis is actually right up here. So that's what I would recommend doing, just kind of drawing it in there, and then you label where you're starting. This right here is the graph of sine x minus 1. So interesting in that example 4. I'm glad I saw that. Negative sine x, it's just going to flip you about the x-axis. So remember, your original graph looked like this. It's just going to take this and go down, and this and go up, right? Because it's just taking those y values. Sine of negative x, it's going to flip you about the y-axis as well. 1/2 sine x, you know what that's going to do. It's going to be a regular sine x function, right? So it's going to look just like this. There's no period adjustment. There is a change, though, in how high it gets. It only gets as high as 1/2 and as low as -1/2. And what does this one look like? Regular sine graph, getting as high as 4 and as low as -4. Notice I'm just drawing it normally and labeling what those are. Let's see what he has. Pretty much the same thing, right? So he's just labeling those as 1/2s and 4s like he should. That's perfect. And notice, and I like that they're side by side like that to have you recognize, oh, he's not going through scaling or anything like that, and neither do I. What you need is rough sketches, because the power of this is to understand what's going on quickly. And what these graphs look like. It's not to graph them. Graphing is not a skill that you need to develop because you have graphing calculators. Quickly assessing what's happening is a skill to have, because what you have is problems that are way more in depth than just graph this. And so we want you to know what that looks like. Sine 2x, you know right away that this is a period adjustment. So because that 2's on the inside, so you can take your original roots, set 2x equal to 0, set 2x equal to pi, set 2x equal to 2 pi, and realize that your new roots are, and I'll put them in red if I can, our new roots are 0, pi over 2, and pi. And so what do? We just draw a regular sine graph and say, you know what, that's pi. This is pi over 2, and this is 0. Hey, I need you to tell me how high where it reaches its maximum. Sure, right in between 0 and pi over 2 or pi over 4. And where is it reaching its minimum? Right in between pi over 2 and pi or 3 pi over 4. Excellent, right? That's what we would do in there. So what does that look like? Just like that. So he's not labeling the mins and the maxes, and that's fine, right? And so all these final examples are just pulling all those ideas together, right? We've done these period adjustments and other ones. So here's another one. And again, you see, this is the same one that he had in the other section. That pi absolutely needs to be up top. He doesn't write it here, but he quickly changes his position right here. So we've looked at that exact one before, probably have looked at this one before too. Sine of 2x over 3. Your immediate thought is, hey, no amplitude adjustment. It's not moving left and right, not moving up and down. The only thing happening is a period adjustment. I can do that. The original zeros are 0, pi, and 2 pi. I'm going to set 2x over 3 equal to them. And what am I going to get? I'm going to get 0. I'm going to get 3 pi over 2. And I'm going to get 3 pi. And that's what he gets. And so what do? Our regular sine function starting at 0, going up and down, ending at 3 pi, hitting here at 3 pi over 2, and we're finished. Right? That's how it should feel going through there. And so here's some sample graphs that he's done, so you can get an idea of how the adjustments come. But you're just going to take it slow and in control. I don't think that there's really crazy homework problems that you're being forced to do. So my challenge to you would be, look at this video and then just go try the homework and see if you can match it. Let me know if you're not matching the answers in the back of the book, and I'll double check them, because if there's mistakes here, maybe there's mistakes in the homework as well. But that's what's happening at the end, is just some sample graphs just to make sure that you know how to go about and do them. So, but probably not an effective use of our time just to study them.